Okay, so this is the AS class. Okay, guys, this is the AS class. The recording for the AS class, right? Okay. So we'll be discussing Unit 2 today, right? We'll be discussing Unit 2 today. And what is the name of the Unit 2? Can anyone of you say? Put on that. Yeah, waves and electricity. That is the name of Unit 2. Waves and electricity. So you know Unit 5. Unit 5 is the longest lesson in the syllabus, right? After Unit 5, the longest lesson is Unit 2. Waves and electricity is the name of that. Waves and electricity. Okay. Alright. Right. Now, under waves and electricity, on this Unit 5 topic, how many subtopics are there? Can anyone guess? No, it's something that I only know. I'm the one who is into these subtopics. So there are 8 subtopics, okay? And in Unit 2 there are 8 subtopics. 8 topics. So our plan for this Unit 2 is to finish Unit 2 by the mid of September. Okay? Finish Unit 2 by mid of September. Therefore, you have to understand this Unit 2. We will be doing the first subtopic today. Right? So that is the lesson plan. I already told this in that video which I sent before. However, that is our lesson plan. For someone who doesn't know. The first subtopic under Unit 2 is write down transverse and longitudinal waves. So initially you should put Unit 2 waves and electricity. Trans 2.1. And in that 2.1 and write down transverse and longitudinal waves. This is the topic. This is the name of Unit 2. Right? Okay. Now, next. So under this unit, that's what we'll be discussing, right? Okay. Hold on. So initially, under transverse and longitudinal waves, you have to understand the properties of these waves. What are those properties? Right. What are the properties of common? What are the common properties of waves? What are the properties that you know of waves?
It acts as a particle and
Yeah, that is true. That is true. Wave can act as a particle. Are you sure that's for waves? It's not for waves. Particle thing, that's not true. Basically, the particle thing is correct if it was for light. Light or an electron, where the photon, they can act as a particle and a wave at the same time. That is it. So, under 2.1, you write down the subtopic. Now, 2.1, transverse and longitudinal waves. Under that, you write down properties of waves. Properties of waves. Okay, right. Properties of waves, right? Okay. Now, and anyway, I'll be uploading this recording, so if you miss any session, you can watch it, right? So, what are the basic properties of a wave? Properties of a wave. Haven't you heard? Wavelength out there. Wavelength is a property of a wave. Then have you heard about frequency? A frequency is also the property of a wave. Amplitude, have you heard? Amplitude is again property of a wave. What about the speed of a wave? That is also again once again a property of the wave. Then the time period. The time taken for one oscillation to happen, that is also a property of a wave. So those are the properties of waves. There are 5 properties of waves. We call them features of waves, properties of waves. In any term that is correct. So those are the main properties of waves, right? So before learning about properties, you have to understand these waves are generated. Waves are formed by oscillating sources. Due to oscillating sources only these waves are formed, right? That is one thing. And these oscillations, they usually travel away from some point. So basically, an IGMA, if you have an issue, right, with the theory, you just tell me, yeah? Okay, right. And I can send you the recording for the first day session. I mean, that's going to be a little bit low quality, yeah? Trust me, that recording is bad. Bad in the sense, it's like the quality is bad, not the teaching, right? The quality is bad because I had uploaded to the Zoom cloud, so the quality is not that good. However, from now on, all of these recordings I will be uploading to the YouTube. So then it would be much more better. It would be at 1080. On Zoom, the issue is the recordings, they are not that clear, right? Okay. Now, for unit 2, waves and electricity, right? We were talking about features of waves. I was telling oscillators, they always travel away from an object, right? Away from an object. So now, under unit number 2, properties of waves, you write down properties of waves.
Yeah.
No. Under properties of waves, you write down the first feature, first property of wave, which is wavelength. 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 Okay. So tell me, what is wavelength? What is wavelength? Yeah, that's very basic, na? No. It is the length of the wave, but it can be defined in a little bit nice manner. But how come? Wavelength means what? The distance between a point on a wave, distance between a point on a wave and the same point on the next cycle of the wave. It's like this, no? So I'm going to take a transverse wave to explain it to you guys, right? So this is a wave. And this is how it's going. The transverse wavelength. Wavelength means what? The distance between this point on the wave and the same point on the next cycle. So this is one cycle up to here. This is one cycle, right? This is one cycle up to here. And then at this point again, the other cycle starts. Same point on the next wave. So this is actually wavelength. Do not draw this yet. Don't draw it yet. We'll get to the point where I represent all the properties in a single wave, and then you can do this straight away. Right? So write down under wavelength, write down the distance between a point on a wave and the same point on the next cycle of the wave. The distance between a point on a wave and the same point on the next cycle of the wave. Right? So it could be either this or even this here. See, between the two troughs, this is the top points like this, they are called crests. Okay, crests, and these bottom points, they are called troughs. So it could be either distance between two crests or distance between two troughs, and even is the length for one wave cycle like this, as you can see in blue color. This distance, that is also the wavelength. See, this distance, this is also the wavelength. This can also be said as the wavelength, right? So don't copy any of this down. Alright, just copy this down as well, because everywhere wavelength is depicted. If I depict other quantities, you would get it confused. Right? Done? Okay. Did you write? Sigma you wrote, right? I assume you have drawn it.
Yes, sir.
Yeah, okay, great. Now, next what we have got is, we have got the amplitude. So put the, write down amplitude. So wavelength was represented by the symbol lambda. Similarly, amplitude is represented by the symbol A. Okay, right. So amplitude A, what is the amplitude? Amplitude means the maximum displacement reached by an oscillation in the wave. So basically it's like this. Again I am going to draw a diagram, a transverse wave. So this arrow shows the direction of propagation of the wave, right? So this is the wave. This is the transverse wave. You have to understand, amplitude means the maximum distance moved by a particle from the equilibrium position. This is the equilibrium position. See, this is the equilibrium position. From the equilibrium position, how much is the particle has gone up? How much of a distance has it oscillated? So that is actually A. That is called the amplitude. That length is amplitude. Amplitude is measured in meters. Wavelength is also measured in meters, right? So did you write down the magnitude of the maximum displacement reached by an oscillation in the wave? Alright, okay. So under amplitude, you write down the magnitude of the maximum displacement, magnitude of the maximum displacement reached by an oscillation in the wave. Reached by an oscillation in the wave. In the wave, right? Okay. Right. So now this is the amplitude, right? This is the amplitude. Just draw it and depict it. This is the amplitude. So like I told you, we have to finish this subsection today. The properties of the wave. I mean, after learning about those 5 properties, the properties of wave part is not over. Okay, right. Like that. Okay. Sigma I also assume that you are done. Right? Next, what we have got is the time period. Write down period, capital T. Period, capital T. Right? What is this time period? What is it? What is this time period?
Time taken for one oscillation.
Yeah, correct. Time taken for one oscillation. So write that down. Time period, you put T, T is the symbol used to represent it. Seconds, it is measured in seconds. The unit is seconds. T is the symbol. Time period is defined as the time taken for one complete oscillation. For one complete oscillation. Right? Okay. That is the time period. That means basically this is one oscillation. See? Up to here, starting from here up to here. See? One oscillation. The time taken for one oscillation to happen. Right? Okay. Now tell me what is frequency. So if that is the time taken or the period is time taken for one oscillation, what is the frequency?
1 over
Yeah, 1 over t, what is that 1? 1 means, frequency means number of oscillations, right, per unit time. Unit time in sense 1 second. How many oscillations are occurring during 1 second? right? Harmonic oscillations for 1 second. So basically, F is equal to 1 over T. This 1 means 1 second. So for T, I will give it as an example, right? You just listen first. For T, let's say you are given the time period. Time period means time taken for one oscillation. Time period is 0.2 seconds, right? That is the time period. Then I am asking what is the frequency. So what is the definition for frequency? Frequency means how many oscillations in 1 second, right? How many oscillations in 1 second. So how do you calculate frequency? You put it to this equation. This is 1 second divided by the time period. So how many oscillations in 1 second? What is 1 divided by 0.2? You get 5. So frequency is 5 Hertz. So actually Hertz means S minus 1. Okay. By time is measured in time period measured in seconds, so this goes up. S minus 1, right? Okay. Right. So for frequency, you write down as frequency. Within brackets, you put the unit. Okay. The symbol is there. The unit is Hertz. H. Capital H. Symbol is there. Hertz. From that you write down frequency means the number of oscillations during 1 second. Number of oscillations during 1 second. And then you build a relationship between F and T. So I don't know, F equals 1 over T as well, right? F equals 1 over T as well. No. Right. Now, the last and final quantity. What is it? So, what have you talked about so far?
Amplitude, wavelength, period, frequency.
Amplitude,
Wavelength, period.
wavelength, time period or period, and frequency, right? Okay. So now what we have is, I tend to appear much more dark in this camera. No. Just think I should adjust the light settings. This might have been the way that I was in the other recording. Yeah. No, but then that means adjust manual. Right. Okay. Oh, this is good. This is nice. Okay. Right. Okay. Now, next what we have got is wave speed. That is the most important quantity, right? So wave speed is basically how fast the wave travels. There's an equation for that. What is that equation? V equals F lambda. That is the equation. What is V? Can you see it? There is a reflection of the light. V equals F lambda. Okay. V means speed of the wave, meters per second. F means frequency. Hertz. Lambda means wavelength. Meters. This is how you measure it, right? Okay. So now this is how you must already know this. You might want to know this, right? Copy it down, sir. Right? So So there's one important fact you should be able to understand with this equation. You have to understand this one. What is it? You have to understand that speed only depends on the medium. Speed in a wave. So wave speed only depends. Wave speed only depends on the medium. Why is that? Speed differs from traveling from light. Right? So, for example, what is the speed of light? No. In a vacuum. Speed of light in a vacuum. Light is a wave. No? It's a type of wave. What is the speed of light in the vacuum? 3 times 10 to the power 8 meters per second. So that is 300 million. Right? That means 300 million meters per second in a vacuum. Right? Next, tell me what is the speed of light in air? Not speed of light. Let's say, yeah, speed of light in air. That is also roughly equal to 3 times 10 to the power 8. But however, when light is moving inside water, it is changing, it is slowing down. We call that, that's why we call it a denser medium. When light comes moving in air, so however, it depends on the medium. If light is moving in another substance rather than water, let's say like mercury, then the speed would be much lower in light than that was in water. So you have to understand, the speed of a wave only depends on the medium, right? So no matter the frequency was increased, let's say, frequency was increased at some point, then the speed won't increase, speed would remain constant, therefore wavelength should decrease. That's what you have to understand. It's like this. So here, this is one wave, then there's another wave. Like this. Can you see? Hikma, you can see, right? Yeah. She can see. Now what is the wavelength of the smaller wave? I'm going to take it as lambda. The frequency will be f here. The wavelength here, so I'll take this as lambda 1, f1, right? It would be lambda 2 and f2, let's say. You have to understand that what? You have to understand f1, sorry, lambda 1 is lower when f1 increases. Why? Speed is constant. Speed is constant. This is for the same medium. So that is why you are getting an electromagnetic spectrum. In the electromagnetic spectrum, waves are moving in the same speed in the air, but they are divided into several variations based on their frequency and wavelength. That's what has happened. Lambda is down, lambda is lower, frequency has increased. See, number of oscillations per second, they have increased. Let's say the time period is 1 second. See, the time period is 1 second, then 1, 2, 3, 4. About 4.5 oscillations here. But here, about 1, right? So see, that's the issue. Here the frequency is low, f2 is low, but lambda 2 is very high. Do you understand? You have to do this. So what I want you to do is, after writing this part down, you write wave speed only depends on the medium. Write down wave speed only depends on the medium. You write it down like that, and then for this one, you write down frequency is higher and lambda lower For the bottom one, you write down frequency lower, lambda higher. Like this you write down. The marker pen seem to be out of ink a little. Alright, Dima has also joined. Dima, the first parts, the first sections, you watch them from the recording. I'll upload the recording tomorrow. So basically, so far what we have done, how many pages do you need? Let me check and tell you. How many pages is one page? One page, one page, 1.5 pages. Yeah. Just leave one side of a page, one page, and just leave 1.5 pages. Right? It's safe if you can leave like one whole, like a koyak, leave karanga, right? That's it. Done? Okay. Right? For all of this, just leave one page, just two sides. Leave just two sides, then it'll be fine. Okay, so listen from next part onwards, right? So actually now, guys, this part is over. Right? This part is now over. I'll just erase it. I hope you are done writing. Just erase it. This part is now over. This is it. Right. So next, what have we got here? Now, a small equation question. Alright. Now, this is a very easy question, right? This is just a really easy question. I'll be sending a question to our group. If you don't have access to the group currently, just send me a message via Zoom. I'll send it to Zoom if you want. But otherwise, I'll be sharing it to the group. Tell me the answer. Just type your answer and send online students. Make sure you convert the units to SI units. Who's Rohan? Yeah, 10 to the power minus 6 micrometers. Milli is 10 to the power minus 3. Micro means 10. Yeah, this is micro. Micro means 10 to the power minus 6. Huh? Okay. Right. Done? Someone maybe send the message. Soon? What is that?
10 to the power minus 7.
Sorry?
1 into 10 to the power minus 7.
minus 7. Not minus 7. 1 the n, 1 minus 7 though. Isn't it 10 into 10 to the power minus 7? That means 1 into 10 to the power minus 6 it should be. Why? Did you convert velocity? 100 centimeters per second?
110 to minus
100 into 10 to the power?
minus 3.
Minus 3. 1, 2. No. Never can.
Centimeters to meters?
Yeah, centimeters to meters per second. Which multiplied by 10 to the power minus 2. What happens? Then it becomes 1 times minus 1. Right? When for the conversions, what is the calculator? Conversion is karala, then you use the calculator.
One 10 to the power 6 per high.
1 into?
10 to the power 6 minus 6.
Correct, right? Okay. Now, this is how you should get the answer. Wave has a period of 1 microsecond. So, time period. First, whenever you are reading a question, even in the exam, this is how you should try, right? First of all, list out the quantities that you know, then the picture will be much more clear. But 1 times 10 to the power minus 6 seconds. Micro means 10 to the power minus 6. That's why I have taken it like this. Okay. Then, next what have we got? We have got 100 cm minus 1. So that is the wavelength. Sorry, the velocity. So V is 100 times 10 to the power minus 2 ms minus 1. Centi or C means centi. Centi means the prefix for 10 to the power negative 2. Right? Okay. Then they ask us to calculate the wavelength. So we know F equals 1 over T. This is the equation we learned it before, right? Like today in today's class, we learned it like in the first half an hour. So you can watch the recording and you'll understand it, right? Okay, right. So that's this equation anyway. We use it here. Then what happens? 1 times 10 to the power minus 6. This goes up. So the frequency becomes 1 over 1 times 10 to the power minus 6. You get 10 to the power 6 F hertz. You know V equals F lambda, right? Then this becomes 1 ms minus 1 equals 10 to the power 6 lambda. So then lambda is going to be equal to 1 times 10 to the power minus 6 meters. That should be your answer. Okay guys? So that is it. Right? Check now? Okay. Now what have we got here? So that is the question, that is the answer to the question, right? Okay. Right. So now we are going to learn about transverse and longitudinal waves. So I am going to erase this. If you didn't understand, just tell me. Right? No issue? Okay. We'll move on to longitudinal and transverse waves. So what are transverse waves? What are longitudinal waves? Alright. What are transverse waves? What are longitudinal waves?
One move horizontally,
Yeah. One moves horizontally, other one moves vertically. No. Yeah. The two words are not horizontal and vertical. The two words are perpendicular and parallel. Right? Okay. So basically, longitudinal waves means waves which travel parallel to the direction of propagation of energy. And transverse waves mean waves which travel perpendicular to the direction of propagation of energy, right? Okay. So we'll be discussing each of them one by one. So we'll break down everything related to them, right? Okay. Now, you understand under this thing, right? You understand under this. Initially, you are put the subtopic transverse waves. So basically, guys, once you are done with longitudinal and transverse waves, we have to understand how to draw graphs for these longitudinal and transverse waves, and then learn about stationary waves. Right after that, we'll be done. This waves part is this 2.1 part will be over, right? So that is our target for today. We have to accomplish it, right? Okay. So under transverse waves, you write down the definition of a transverse wave first. So what is a transverse wave? Transverse wave is a wave in which particles oscillate perpendicular to the direction of propagation of energy. Oscillate perpendicular to the direction of propagation of energy. Right? Okay. Now you have to understand, for transverse waves, I was telling particles propagate perpendicular direction of energy. So what is this direction of propagation of energy? So listen up closely, right? So in a transverse wave, you have to understand, this is how it happens, huh? You have to understand that this was the equilibrium position, and already this was something called the equilibrium position, right? So in this equilibrium position, there are particles everywhere. When a transverse wave is moving, or when a rope is moving, the rope is like the best example for a transverse wave. Just take it and you just make it go up and down, right? One point fixed, it's much more easy. If one point was fixed or not, doesn't matter. A point doesn't need to be fixed or not. If you just move up and down, move something, it is going to be a transverse wave. The particles are going to oscillate perpendicular to the direction of motion. So what particles then? What are those particles which are moving perpendicular to the direction of oscillation? Propagation of energy. There are particles located like this, right? In the atmosphere. So those particles basically move up and down. Initially, this is stationary. This is moving a bit. It's moving further. Then this is moving like this. Then so this is how this occurs, right? And then this comes to here. This comes to here. This comes here. And then this goes back here. This comes down here. And then this is not oscillating again. Here goes up. Goes up like this. Goes up like this again. So that is how this occurs. Can you see that the particles are oscillating perpendicularly to this direction of propagation of energy? This is the direction of propagation of energy. Energy propagation, huh? See, direction of propagation of energy. So energy is moving in this direction. Particles are moving up and down. Particles are moving just up and down. Energy is being transferred like a curve. Right? What happens in the next second? In the next second, this particle goes down. This slowly gradually come down. So the wave is going to be like this. Understood? So every second it is changing. So basically, if I concentrate only on a single particle, what happens? If I concentrate only on a single particle, you can see that the particle is moving up to here, then up to here, then up to here, then back again here, then here, and back like this. It's going up and down momentarily. Up and down, up and down, up and down. Then increasing. Likewise, that is what's being happened. Right? So keep that in your mind. That is what motion means. That is what particles propagating means. So the particles are propagating However, the particles, they are not moving. Huh? Some students have the idea energy is like this, energy is what which is moving like this. No, particles are just a stepping stone for the energy to move. It's like that. Energy is moving those particles as a stepping stone. Keep that in mind, right? Okay. You don't need to draw any of these, huh? Right. So after this, what we have is, we have got the this propagation of the wave, right? So this is usually the structure for the wave propagation. This is a regular transverse wave, like this. Like the amplitude can vary, it doesn't need to be this pointed, right? So this is it. This is called a crest. These are crests, and these are troughs, right? Troughs. So, and this depicts the direction of propagation of energy. See, this is the direction of propagation of energy, right? Okay. And the direction of vibration, as you can see, it is perpendicular to the direction of propagation of energy now, right? So note it down. Under transverse waves, you just note this down. So if you have any questions, just send it to me via the chat or just let me know.
Sir, you're muted.
Yeah, I was muted the whole time, no? Right. No, I was just basically saying, oh, you guys, did you guys write all this down?
Yes.
Alright, okay, great. Beema, I also hope that you have written down. If not, like, you can always watch the recording again, right? Right? Okay. Now, here, what I was saying was, this, we were talking about examples for transverse waves, right? So, do you know any examples for transverse waves? Hikma, you say, if you know, just straight away say it to the microphone. Yeah. So you said ropes, no? Water waves. Yeah, water waves is also correct. Now water waves, you got one thing. Water waves, that is correct. What else? Anything comes to your mind? At least send it in the chat. Send it in the chat. Nothing? It's really easy. Have any of you played guitar? So, right. So in a guitar, the wave that is produced when you pluck a string, that is a transverse wave. Okay? More and more insects coming. That is, they are coming to the light or something. Right? That is the reason they are coming to the light. So, okay. Now, next. What we have got is next. So I told you the equation, sorry, not the equation, the examples for transverse waves. One thing that we know is examples for transverse waves. We know about water waves. Water waves are examples for transverse waves, real life examples. What about waves on a string? So means it comes under waves on a string, right? Waves on a string, right? Okay, because there's a glare here, I'll just be writing it underneath now. Then after waves on a string, what have we got? And remember, electromagnetic waves. All electromagnetic waves are transverse waves. So what are electromagnetic waves? We've got radio waves. After that, microwaves. After that, infrared. After infrared, visible light. After visible, UV, ultraviolet. After that, X-rays. After that, gamma rays. And then there's one more thing. There's something called cosmic rays. You don't have it in your syllabus. All of them are electromagnetic waves. So all that comes under transverse waves, right? I'm just going to write electromagnetic waves, huh? Then next, what have we got? We have got one thing. Like this is a little bit unique. Have you all heard about seismic waves? Oh, seismic waves? Seismic?
For earthquakes, right?
Yeah. For earthquakes, that's what we get. Seismic waves. So, what are these seismic waves? Waves which are traveling on the surface of the earth during an earthquake. There are two types of these seismic waves. We've got seismic waves, so there are two types. What are those two types? S type and P type. These are the two types. So one of these, out of these two types, one of them is a transverse wave, the other one is a longitudinal wave. Can you guess? What is the shape of a transverse wave? So yeah, it's like this, no? See, it's like this. So when we turn this, if I was to flip this S, it would be S, right? Do you understand? If I were to flip this S, which was like this, if I were to flip this like this, it would be like this, no? After flipping. Then you have to understand and remember, transverse waves, S-type seismic waves is the transverse wave. Got it? Right? So therefore we can say another example of transverse wave is S-type seismic waves. Okay, so note this down. As examples, some examples, you know, write this down. These are the examples for seismic waves, for transverse waves. So now transverse wave part is over. Next, you write down longitudinal waves. Guys, give me 2 minutes, huh? Now, write down longitudinal waves. I'm going to erase this. Now, longitudinal waves. What are longitudinal waves? The definition. Write down. Under that, write down the definition for longitudinal waves. Waves in which the particles oscillate, waves in which the particles oscillate, waves in which the particles oscillate parallel to the direction of propagation of energy. Right? Waves in which particles oscillate parallel to the direction of propagation of energy. Right? So basically you have to understand, in these types of waves the particles are moving not up and down. In transverse waves they are moving like this. In longitudinal waves, however, they are moving side to side parallelly to the direction of propagation of energy. Right? Got it, sir? That is how you should understand this. Okay, right. Now, next what we have got here, other than thing, you have to draw a transverse wave, right? I mean the best way to draw a transverse wave, longitudinal wave, the best way to draw a longitudinal wave, there are two ways to draw a longitudinal wave, right? This is one way, and then there's another way. I'll teach both of them to you. Right? It's like this. So basically, we are taking a slinky. There's something called a slinky, guys. Okay, something called a slinky. If you search it online, you'll get it. Something called a slinky. We call it slinky. Yeah. Right? I'll just show it to you. This slinky. Right? I'll show it to you. Hold on.
I've seen.
You have seen the slinky? Alright. This is what a slinky looks like, okay? Slinky spring. Okay, so look. Have you seen this thing, guys? Images. No, this way. Have you seen this? See? Something like this. Yeah, you have seen, right? Okay. So, this is called a slinky. You can oscillate this slinky side to side. So, you keep the slinky, hold it up from this side, and then you just move it side to side like this, right? Then what happens is, this is the motion that you can observe there. These are like the string of the slinky. At one point they are closer together to each other, and then they will be spread further apart, and after that again closer to each other, and then spread further apart like this. I don't know whether this is clear. Yeah, it is clear. So if I were to look at this motion from the top, there is something called wavefronts. There's something called wavefronts. So basically a wavefront is how we see a wave when we look at it from the top. So if I were to draw wavefronts for this, it would be like this. So closer together, wavefronts are also close together. Then apart from each other, away from each other, wavefronts also away. Again closer together. So see, wavefronts are closer to each other again. Then apart, far away. Right? This is how wavefronts would look like. So actually guys, these points, this is a compression, and this is again a compression. This part, compression. Then compression. What about here? This is a rarefaction. Compressions are the points where particles are closer together and the pressure is maximum. Rarefactions are the points where particles are away from each other and the pressure is minimal. Right? Okay, so that is what you have to know here. Right, guys? Okay. So, draw this and copy this down. So just mark, this is from the slinky, and these are wavefronts, right? You put wavefronts and then within brackets you write down how we see wave from the top. Even for transverse wave, we can draw wavefronts. How we see waves from above. Right? Okay. Right. So after this point, we will be writing definitions. So defining what are these compression and rarefaction. So underneath this diagram, you write down compressions and put an arrow like this, and then you write down the definition for these compressions. What are compressions, right? So put compressions. Compressions, right? Okay. Compressions, you put it as compressions and then write down points in a longitudinal wave, points in a longitudinal wave, points or areas. I think areas is much better. Areas in a longitudinal wave where the pressure, where particles are closer to each other, and the pressure is maximum. Compressions are the places in longitudinal wave where the particles are close to each other and the pressure is maximum. Then rarefactions are the areas in which particles are away from each other and pressure is minimum, right? Same thing in the other way. The pressure is minimum. Right? Okay, no? Right. So now we have to write down examples for these longitudinal waves, similar to what we do for transverse waves. We have written examples for longitudinal waves, right? Okay. Now tell me, guys, what are the examples? What do you know as in longitudinal waves? What are longitudinal waves that you know?
Sound wave.
Yeah, sound wave is a longitudinal wave. That is correct. Other types, I just told you a seismic wave. What is that?
P-type.
P-type seismic waves. Okay. We got sound waves, seismic waves. What can you say about ultrasound waves? Are they longitudinal or transverse?
Longitudinal.
Yeah, they are also longitudinal. Okay. Ultrasound waves are also longitudinal, right? Okay. So under examples, you just write down examples for longitudinal waves, sound waves, and P-type seismic waves. Right? Okay. Now, ICMA in the group, I'm going to send a question, right? So you guys just get this question done. So the second question. So for those who are following the recording, pause this video now and then go to the group, look at the second question that I have sent. It's an MCQ question, right? Okay. Well, on left? Okay, you're saying C. Yeah, I am saying C. What else?
The amplitude be 2 centimeters?
Graph shows no. Right, we'll wait till Hikma. Send me your answer to the chat. This group of ours. Not the group, I mean not the WhatsApp one, just this Teams one. If you have taken, send me the answer. Right, you are just reading. Just I'll give you time. Right, we have time. We have like another 40-45 minutes. So we only have after this question. We only have. That's not the answer. Just read it again. So after this question, we only have to do stationary waves. So then I think we'll be safe. So we'll be done with 8.1. We'll be on track, right? So for this class 2, right after we are halfway done through the lesson, unit 2. We'll be discussing a set of questions, right? So basically, that's what we'll be doing in the class. In the class, we'll be discussing this thing, questions. Yeah, that's it.
Either transfers or
Yeah. So make sure you read it very carefully, right? So this is a type of question you might get in the exam. These types of questions, it's a bit tricky, you know, that's why. Right? Okay. Right. Hikma, did you got an answer? I don't know how I put this in, I can't take this out now. It's in the wrong finger.
try away.
Huh? Okay.
Sir, is it 8?
Yeah. You have sent the answer. You have sent it 8:51. Oh, it's been 1 minute. Yeah, it is 8. The answer is 8. Okay? That is the answer. Can't seem to take it up. I don't know how it went in though. Sheesh. Okay. Okay. Right. Now, I have a responsibility to do the class. I am not letting that go. Okay. Now, you have to understand about stationary waves. Don't concentrate on the ring now, right? So, okay. Right.
Live with it now.
Huh?
Live with it now.
Yeah, I think I can live with it. Might be coming off. Right, Ikwa, do you know I put my ring in the wrong finger? Right, okay. Now I'm back. I'm back now, okay. Energy is back. Energy is back, right. Now, part A is over. We're done with part A. Right now, next, what we have is, we have this graph. We have a graph of stationary waves, right? Not a graph means it's not like a graph that you think. We have learned about stationary waves plainly. So write down the topic stationary waves. Now we have learned about initially what did we do? We learned about the properties of the wave. There were 5 properties. Can you guys remember those 5 properties? Okay. You say one.
Wave.
Then
Time period.
Then
Amplitude.
Right. So we have got wavelength, time period, amplitude. Hikma, you say the remaining 2. Instead of wavelength, time period and amplitude. Wavelength, time period, amplitude. Tell me 2 other quantities. Quickly. Wavelength, time period, amplitude. 2 more quantities instead of that.
Frequency?
One final one.
Wave speed?
Wave speed, correct, right. So we learned about those 5 and then we moved on to learn about transverse and longitudinal waves, right? So what are transverse waves, what are longitudinal waves? You tell me transverse. Direction of propagation of energy.
Yeah.
Right? Now Hikma, you tell me what are longitudinal waves?
Waves in which the particles oscillate parallel to the direction of propagation.
Direction of propagation of energy, correct, right? Okay. So basically, that is it. You have to understand those things. Then we learned about how they are represented, how to draw, and what is actually happening, how the particles are oscillating. And the other thing is we learned about the examples which are coming on transverse and longitudinal, right? Now, okay, ICMA you tell me S type or P type, longitudinal waves, transverse waves, seismic waves.
Transverse.
What is transverse? S type or P type?
Yes.
S type is transverse, P type automatically becomes longitudinal. Okay, right. The other thing is, I forgot to teach this to you guys. Under longitudinal waves, under sound, right? So, have you ever wondered actually how is sound being propagated? This is how the sound is propagated, right? What is that? No, yeah, that's correct. It's actually represented like this. In air, it is not going like this. Yeah.
The wave gets bigger, right?
No. That is something else. That is intensity. Right? That is intensity. It's like, it's something else, right? However, it becomes more spread out. That's correct. However, if I want to shout at here, from here, right? This is my mouth, right? So, I'll show you how the wave is going in this direction. I am speaking from here. So, a person standing here can hear me as well. So, I'll show you exactly how this happens. So, this is me. This is my mouth, right? Okay, maybe this is my mouth. Okay. So now I speak. So the particles near the surface of my mouth like this. What happens? They get the sound. So they start to vibrate, right? And then this vibration, this gets spread out. The particles are now spread out. Then at here, again they compress. See, again they are compressed. And then again they get spread out. I'll put an image of this to the group. Again they are spread out. See. Otherwise you can't see this that clearly from this thing. And then again, see, they get compressed. Here compressed. And then only again compressed. So then okay. And then only this ear control it. Okay. This is the ear. Right, don't judge. Okay guys, this is the ear. I just mark it as the ear while you guys will think this is something else. Ear. This is the mouth. And this is how sound is propagated in air. How sound is propagated in air. So the sound is using air particles as a medium of propagation, right? So that is the only reason you can hear me in this Zoom class. So the sound waves, they vibrate like this, they hit the camera here, hit the microphone here, and then what happens? The signal gets to a tower and then it gets converted. You can hear my sound from the speakers. That's what happens, okay? You got 40% off today on Domino's.
It's KC deal, I think.
Today?
Yeah, there are also having KC now.
Every Wednesday?
No, just today.
Just today?
I think.
What's the deal?
Today is Thursday.
Yeah, what's the deal?
I have no idea.
Oh, it's
good deal and after that.
It's being recorded. See, that also being recorded. So KFC, if you are seeing this, make sure you hit me up. Right? I'm a free promotion right here. Okay. Here, like, okay. Right, so Hikma, I'm going to upload this to the group, and those who are following the recording, check your group. You can't see this clearly, no? Right, I'm going to share it to the group, our AS group, no? gonna crop it. Right. How sound waves are propagated in air. Okay. Right. So I have sent it to the group Hikma. Just check it out. You'll be able to see it. Okay. Nice. Now, next what we have got is here for this. So I'm going to erase this. This is how the sound waves are propagated. So just keep it in your mind. These are longitudinal waves, and if you ask to find the wavelength of a longitudinal wave, this is the wavelength, the length between two of these things. Okay, right. So you don't need to copy this down. This is for your own extra knowledge. This is good to know, good to have enough idea on how this sound thing works. Okay. Now, this is what we have next. Also have yeah. Now write down stationary waves. Under stationary waves, this is what we have to understand. What is a stationary wave? Stationary wave is a wave occurring if two transverse waves, not exactly transverse waves, if two waves which are having the same frequency are moving in opposite directions in the same medium meet. A stationary wave or a standing wave is produced. Right? Okay. I'll explain it to you like this. So it's like this. Imagine I have a piece of a rope. Right? I connect it to this board. Right? So basically I'm going to connect it to certain point. Right? Imagine this is the piece of rope. I'm going to connect it to this point. Right? Then what am I going to do? I am going to hold the end of this rope and then move it up and down. What would happen? Initially, you will see something like this. This is what you will see initially. Right? Initially, you will see this wave, this rope moving up and down like this. Right? This is how you see it now. This rope would be moving up and down like this. Okay? Right. Next, you have to understand what happens next. Once this one goes and hits here, it's going to come back reflected. Right? So then what's going to happen? Then what will happen is, you have to understand this thing right here. The wave that you are going to see is going to be like this. One is like this and then the other one is going to be like this, but you are still moving this thing up and down. That's only what you are doing. That's the only thing that you are doing. But this is what's actually happening. Right? So for this to actually be true, this won't happen exactly like this, because the side that you are holding, it's not exactly stretched. However, if we can stretch this side, this type of thing would occur. Otherwise, you can do this at home, but then exactly this won't come, right? Something similar to it would come, unless you get the maximum extension for this side. You stretch it out as much as possible, right? Increase the tension of the rope as much as possible, then it will come, right? Okay. So, stationary waves, there's no net propagation of energy. Why? It is going to just keep it goes and then it comes back reflected towards us again. There's no net propagation of energy. That means it appears to propagate energy, but it is actually not happening. Right? Okay. So if you are asked to draw a stationary wave, we'll be anyway learning about this in depth in the next couple of lessons, right? You need to move, when we are moving on, we'll be learning in depth about this. So for now, you just draw something like this. Okay, I'll just stand up and do it. This is the reflected one. So these loops, we call these the loops. One of these are loops. They have to be roughly equal. Loops are usually equal. That's the reason. The distance between two loops is the wavelength. Always, always wavelength is the distance between two loops. This corner point, or the point where there is no displacement, the displacement is minimum, is called a node. These are called nodes. Node. All of these points, they are called nodes. And the points where displacement is maximum, and the pressure is minimum. So at nodes, the pressure is maximum, right? Because they are compressed. These are called antinodes. So antinode means this point. Antinode. So all of these points, they are antinodes. At antinode, the displacement is maximum. Right? This is antinode, and this right here, this is also an antinode. Right? Okay. So let's say this is the total length is L of this string up to here. The total length is L. I am saying. So tell me what is L in terms of lambda. If you understood this, you can tell that. Right? L in terms of lambda. So basically, L equals how much lambda? L equals, you should be able to understand that L equals 2 lambda. Why? 2 loops means 1 lambda, 4 loops mean 2 lambda. Then what is 1 loop? What is 1 loop? Lambda by 2, right? Lambda by 2. You have to understand that. So under stationary waves, you put stationary waves and then straight away draw this thing. Just make sure when marking L, you mark it only up to this one. Like you can put any number of loops, right? As long as it is convenient, you can put it. So we'll be learning about, now we are done with 2.1 guys, we'll be moving on to 2.2. So write down the topic for 2.2, you write it down as interference and stationary waves. Right, so pause the recording, then write down the topic interference and stationary waves, and underneath the first subtopic of 2.2, interference and superposition of waves. Right, so once we are done up to 2.4, we'll be discussing more questions in the class. We'll take a separate day, do only questions that day, discuss them. So try to get the maximum you can out of the live class itself or the recording itself. Try to get the maximum. Get your notebook up, don't be lazy, don't put this recording on top of a bed. You have only got approximately 3 months for your exam. Right? Okay, so that means you are meeting me only another how many weeks? 12 weeks roughly. Right? So try to get your maximum. Okay, right. Now, under interference and superposition of waves, right, so put the first subtopic under 2.2, interference and superposition of waves. Okay, right. Now, what is interference? What is interference? Interference is something which occurs whenever 2 or more waves combine to form a resultant wave. Right? So, interference is not the quantity that we are going after. It's not that special. It's special, but then we just say interference occurs. Interference occurs when 2 or more waves combine to produce a resultant wave. That's it. Superposition means literally, by the definition itself, positioned over. Superposition. Positioned over. Right? So it's basically like whenever waves interfere and combine, they do so according to the principle of superposition. So what is this principle of superposition? Can you remember? The principle of superposition is whenever 2 or more waves combine, their resultant wave, right? The amplitude of the resultant wave would be equal to the algebraic sum of that of the individual waves. So So basically, let's say there are two individual waves like this, right? Like a pulse, imagine a pulse is moving. Straight away up, it's moving like that, okay? A pulse. It is moving in this direction. Then there's another pulse that is moving in this direction, right? You have to understand, the amplitude here is A, and the amplitude here is also again A, right? So then, what would happen when they come together? The resultant pulse would have amplitude of 2 amperes. Then, they would again be moving in their separate directions, right? Now this would be moving in the other side, and this would be moving in this side. That's what's going to happen, right? So, this is called constructive interference. That means combined constructive. The amplitude of the resultant wave, the resultant one, is larger than the amplitude of that of an individual wave. Larger than one individual wave. This is constructive interference, right? Then we have got destructive interference. What is destructive interference? Basically, destructive interference means, imagine the pulse is like this, coming in this direction, then there is another pulse going in this direction, right? Okay. So this is A, this is again A. What's going to be the resultant wave? The resultant wave is displaced like that. There is no resultant wave. I mean, when they combine, they like destruct. There is no wave. And then after they move, after they pass distance, this is what's going to happen. A, and then this is going to go like in this direction A. So this is destructive interference, right? So in destructive interference, you can see that the wavelength of the amplitude of the resultant wave is less than that of the amplitude of an individual wave. So basically, imagine the amplitude is 2A here, that means A here, in it would be A, right? Understood? Right, okay. So that is it. So under interference and superposition of waves, under that topic, you write down interference occurs when two or more waves combine to produce a resultant wave. Two or more waves combine to produce a resultant wave with a new amplitude. Right? Right. Next point you write down, whenever waves interfere and combine, they do so according to the principle of superposition. Right? What do you write down? When waves interfere and combine,
They do so according to the principle of superposition.
Right? Okay. Now, what is this principle of superposition? So you write this down in a separate piece of separate color pen. If you have one, okay. So you can put like this, like epsilon. I don't know what do you call this. Acceleration. Something. I don't know, something. Just if you have another color pen, you can write it down or somehow highlight this. This is the principle of superposition. Okay, so this is the principle of superposition. When two or more waves cross at a point, when two or more waves cross at a point, the displacement at that point, the displacement at that point is equal to the sum of displacements, equal to the sum of displacements of the individual waves, sum of displacements of the individual waves. Okay, of the individual waves, right? Now copy this down. Copy this down. Those who are watching the recording, they pause the video and copy it down. Right? Okay. Guys, give me I sent him a message. He's from another country. Right? From Bahrain. There are like the time difference is I think like 1.5 hours or 2 hours, 2.5 hours before us. So then for him it would be 9:30, would be like 7 something. So then I have asked to give me half an hour, 10 to 20. I have to go to university now. Right? Okay. Now next what we have got is this thing, guys. So you understood constructive interference, destructive interference. Constructive interference happens when the resultant wave has a large amplitude than any other individual waves, and destructive interference happens if the resultant wave has a small amplitude than that of any individual waves, right? Okay. So next what we have is we've got something called coherence. So after we learned about coherence, we are like 1/4 down with the 2.2 part as well. 1/4 of the 2.2 part will be over. So after coherence, today's class will end. Coherence is the last thing that I'll be teaching today for you guys. Okay, right. So under coherence, you have to understand something like this, right? Remember, interference of two waves is only possible if those two waves are coherent. If they are not coherent, interference is not possible. Why am I saying something like that? See, if two waves are said to be coherent, then if I am to say these two waves are coherent, you have to understand they should have a constant phase difference. So what is this phase difference? For now, what is phase difference? Just tell me. What is phase difference?
Different wavelength.
No, phase difference, not phase different. What is phase difference? Right. Okay. If I were to teach you phase difference, because anyway we have phase difference next, right? Forget about phase difference. Phase difference, if I teach you now, like I would only be able to teach you a week now from the knowledge that you have so far. Then you won't understand it fully when I teach it separately. Because after this part, later on you get separately for phase difference, right? So for now, you just understand phase difference means they have if two waves are said to be coherent, they have the same time period and they have the same frequency. Think of it like that, right? Similar time intervals. Think of it like that. So these two waves, just try to understand from the diagram. You'll probably understand this is easy. There's one wave like this, okay, right? And then there's another wave like this, right? So I combine them, there would be a destructive interference, right? This to this cancels off, this to this cancels off, this to this cancels off. The interference would be destructive, but somehow this allows interference, right? This lets interference happen, okay? So these waves are called coherent. So for interference to occur, the wave should be produced by a coherent source. These two waves are coherent. We can say they are coherent. However, let's say the other type, in the other waves, Can you see? This is the other way. Like this and like this. I'm taking it here. And then the next wave that we are going to combine is like this. It's like a note produced in a violin. It's like this. Like this. So now they do not have constant phase difference. Now do you understand? Get an idea on what is phase difference? You somehow get an idea like a wobblish, sluggish, not very sure, unclear idea. For now, keep that in your mind. Can you see that these two waves are not coherent? Coherent, they are not coherent. So we say non-coherent. Right? So these two waves, we can't use them for interference. No interference. Why? You have to know, for interference to occur, the waves should be produced from a coherent source. Understood? Okay, right. So you put the topic as coherence. Write down the topic as coherence, and then underneath that you write down interference is only observable. Interference is only observable if produced by a coherent source. A coherent source. Right? Interference is only observable if produced by a coherent source. Then next one you write down, waves are said to be coherent if they have, number one, in point form you write down, there are only 2 points. Number one, is it the recording on? Yeah, I have switched the recording on, luckily. I thought I had not switched the recording on. Right. Number one, waves are said to be coherent if they have, number one, constant phase difference. You just write it down. This for now, I will be explaining it to you separately. We have a separate topic for phase difference and this thing. Right? Okay. Phase difference. Constant phase difference. Number two, same frequency. Difference and frequency. Okay. Constant phase, number two, frequency, right? Now copy this down.
Excuse me, sir.
Yeah. What is it, Hikma?
Could you send a picture of the board?
Alright, sure.
Because it's not.
Yeah, I'll send. I'm sending this to you as a personal message, huh? Right, okay. Your parents are asking where you are.
We don't ask for lots of
Which parent does that with the? Tell that to me. Done? Okay. So Ikma, I have sent this to the group. You can also get it done. Right. So guys, that will be for the recording session today. So we have done 2.1 of the second lesson and finished about 1/4 of the second part, unit 2, 2.2 as well. And so we are actually in par with our speed. Yeah, we are at a good speed. So we can probably get this done, get this lesson done as planned, right? So just remember, the other class for our AS is on Sunday at 11 a.m. in the morning, 11 to 1 p.m., 11 a.m. to 1 p.m. we'll be having the class. So in there we'll be discussing unit 2. We have already done one unit. So if you want the recordings of that, for those who are watching the recording, you can just send me a message, right? So that is it. That is it for today. We'll meet back again on Sunday, right? So those who are joining for unit 1 on Thursday again, we'll meet at the same day, right? So I'll be updating the time on when are we going to meet on Thursday, right? Okay, so goodbye guys, right? Goodbye for the recording people. Okay, done.